Cast iron stoves in every other cabin along Wolverine Creek had already shattered like glass in the -60-degree cold, their metal frames splitting with sounds like gunshots, as the February blizzard of 1891 reached temperatures no one had survived before. Inside Jacob Harlan's lone remaining cabin, his strange octagonal stove continued burning steadily, its segmented plates shifting and breathing with each temperature change, the flexible joints he'd spent 3 years perfecting, allowing the metal to expand and contract without destroying itself. When rescue parties found him 3 weeks later, alive and warm while 17 of his neighbors had frozen to death beside their broken stoves, they discovered an engineering principle that wouldn't be formally recognized by science for another 40 years. Before we reveal how one self-taught blacksmith solved a problem that had killed hundreds of frontiersmen, let us know where you're watching from and hit that subscribe button if you want more untold stories of impossible survival. The temperature gauge outside Fort Benton's weather station snapped at -58 degrees Fahrenheit on February 11, 1891. The mercury had contracted beyond the instrument's lowest marking, rendering further measurement impossible. Across the Montana Territory, the cold descended like a physical weight, turning breath into ice crystals before it left the mouth and freezing exposed skin in seconds. But the true killer wasn't the cold itself, it was what the cold did to the cast iron stoves that every frontier family depended on for survival. Margaret Hoffman heard the first explosion at midnight. The sound came from the Petersons' cabin, a quarter-mile away, a sharp crack like a rifle shot, followed by screaming. Their stove had split down the middle, the sudden failure releasing smoke and flames into their living space. By dawn, 6 more stoves along Wolverine Creek had suffered catastrophic failure. The extreme cold had caused the cast iron to contract so severely that the metal simply shattered, especially when hot fires inside met the Arctic temperatures outside. The thermal shock was too much for rigid iron to withstand. The rescue parties that set out from Fort Benton on February 28th found a valley of death. Cabin after cabin contained frozen families, their stoves destroyed, their last moments spent trying to burn furniture and clothing in desperate attempts to stay warm. The Peterson family, the Bradfords, the McKinneys. 17 dead in total along just one creek valley, but at the far end of Wolverine Creek, smoke still rose from one chimney. Jacob Harlan's cabin stood intact, warmth radiating from within. Inside, they found Jacob tending to what looked like no stove they'd ever seen. Instead of a traditional rectangular firebox, his stove was octagonal, built from interlocking plates that seemed to float independently of each other. Strange joints connected the segments, allowing visible movement as the metal expanded and contracted. The rescue party leader, Captain William Morrison, later wrote in his report, "The stove appeared to breathe with the heat, each plate shifting slightly, but maintaining perfect seals." Harlan was in good health, his cabin warm, his stove showing no signs of the catastrophic failures we witnessed elsewhere. The impossible had occurred. While every other stove in the valley had succumbed to thermal shock, Jacob's creation had survived 21 consecutive days of the lowest temperatures ever recorded in the territory. The rescue party gathered around the strange stove, feeling its warmth, watching its plates shift and settle with each change in the fire's intensity. They had discovered something that challenged everything they knew about metal, heat, and survival. But understanding how Jacob Harlan had achieved this miracle required going back 5 years to another February night, when conventional thinking about stove construction had cost him almost everything. The story of the stove that saved his life began with the stove that had nearly ended it, and the obsession that grew from that near-fatal failure. February 19, 1886, started with Jacob Harlan and his younger brother Thomas huddled around their cast-iron stove as temperatures plummeted to -42 degrees. They had built their cabin together the previous summer, 2 Pennsylvania blacksmiths seeking fortune in Montana's fur trade. Their stove was the best model available, shipped from Street, Louis, at considerable expense. They fed it constantly with split pine, maintaining a roaring fire against the Arctic cold, pressing in from all sides. At 3 in the morning, Jacob woke to a sound like breaking bones. The stove's front plate had developed a hairline crack, visible in the firelight as a dark line spreading across the glowing iron. He watched in horror as the crack widened, the metal groaning under stresses it couldn't accommodate. The temperature differential between the superheated interior surface and the frozen exterior face had created forces beyond what cast iron could endure. Physics was tearing their lifeline apart. "Get the blankets," Jacob shouted to Thomas, recognizing they had minutes before complete failure. The brothers grabbed their bedding and supplies, backing toward the door as the crack spread across the stove's face. Then came the catastrophic failure. The front plate split completely, sending burning logs rolling across the wooden floor. Smoke filled the cabin instantly. Fire spread to the walls as the brothers fought to escape through the door, which had frozen shut. Jacob threw his shoulder against it repeatedly, while Thomas tried to smother flames with a blanket. They escaped seconds before the roof caught, stumbling into the -42-degree night as their cabin became an inferno. They survived by reaching an abandoned dugout shelter a mile away, losing several toes to frostbite in the process. Thomas would walk with a limp for the rest of his life. But as they watched their cabin burn from that freezing shelter, Jacob's mind wasn't on their losses. He was thinking about metal, about expansion rates, about why iron that could withstand forge temperatures had shattered from simple cold. The contradiction obsessed him. The same material that formed railroad tracks and steam engines had failed from temperature alone. Over the following months, as the brothers rebuilt, Jacob began studying every stove failure he could document. He discovered a pattern that frontier engineers had largely ignored. Cast iron's crystalline structure made it strong but brittle. When heated, it expanded. When cooled, it contracted. But when one side was heated to 500 degrees while the other side faced -40, the differential created internal stresses that exceeded the metal's tensile strength. The iron literally tore itself apart, trying to be two different sizes simultaneously. The problem seemed unsolvable using traditional approaches. Making iron thicker just delayed failure. Using different alloys helped marginally, but didn't address the fundamental issue. The standard solution was simply to replace stoves when they cracked, accepting failure as inevitable. But Jacob couldn't accept that answer. Somewhere in his blacksmith's understanding of metal behavior lay a solution. He just had to think beyond how stoves had always been built. Jacob Harlan spent the summer of 1886 traveling between failed homesteads, examining stoves like a detective studying crime scenes. At the Garrett Ranch, he found a stove that had split vertically, the crack following a perfectly straight line where thermal stress concentrated. He measured the thickness 3/4 of an inch of solid iron, torn like paper. At the abandoned Mueller cabin, he discovered a firebox where the top plate had actually bent upward, warping from repeated heating and cooling cycles until it no longer sealed properly. Each failure taught him something new. He filled notebooks with sketches and measurements, calculating expansion rates and stress points. Iron expanded roughly 0.06 of an inch per foot for every 100 degrees of temperature change. In a stove experiencing 800-degree differentials, that meant nearly half an inch of movement in a 4-foot stove. But cast iron couldn't stretch half an inch. It would break first, and it did, repeatedly, killing families across the frontier. The mathematics were merciless. Traditional stove design assumed uniform temperature, but reality was far different. He borrowed surveying equipment to take precise measurements, discovering that stove surfaces could vary by 600 degrees across just 12 inches. The fire-facing surface expanded, while the room-facing surface contracted. Corner joints experienced rotational forces as different plates tried to move in different directions. Every weld, every rigid connection became a potential failure point. In September, Jacob visited Fort Benton's small library, searching for engineering texts. He found a German treatise on bridge construction that discussed expansion joints, the gaps built into long spans, allowing metal to move with temperature changes. Railroad engineers had solved similar problems by letting rails slide at connection points, but nobody had applied these principles to stoves because stoves were supposed to be solid, monolithic, unchanging. The very rigidity that suggested strength was actually the fatal flaw. His brother Thomas, still limping from frostbite, watched Jacob's obsession with concern. "You're trying to reinvent something that's worked for 100 years, he argued one evening. But Jacob showed him the death records. 17 families in their county alone had died from stove failures in the previous decade. The territorial newspaper called them heating accidents, as if the failures were random misfortune rather than predictable engineering disasters. The revelation came while watching a spider's web one morning. The web survived wind that would shatter rigid structures because it flexed, each strand moving independently while maintaining overall integrity. What if a stove could do the same? What if, instead of fighting thermal expansion, the design accommodated it? Let the metal move. Let it breathe. Build flexibility into the very structure that everyone insisted must be rigid. By winter's approach, Jacob had filled 3 notebooks with revolutionary designs: segmented plates, floating connections, expansion joints, hidden within decorative elements. A stove that could expand and contract without breaking, that could be 2 different temperatures simultaneously because its parts weren't fighting each other. The mathematics supported it. The physics demanded it. Building a forge capable of precision metalwork in frontier Montana required resources most men would consider impossible to obtain. Jacob Harlan didn't care about impossibility. In March 1887, he began transforming a corner of his rebuilt cabin into something resembling a master blacksmith's workshop. He constructed a specialized hearth using fire bricks imported from Chicago, each brick wrapped individually for the 1,000-mile journey. His anvil, a 200-pound Swedish model, cost more than most trappers earned in a season. The specialized materials proved even more challenging to acquire. Traditional cast iron wouldn't work for his revolutionary design. He needed specific alloys, steel with precise carbon content for the flexible joints, high-grade iron with controlled impurities for the plates. He corresponded with foundries in Pittsburgh, sending detailed specifications that puzzled metallurgists. One supplier wrote back asking if he was building artillery pieces. Jacob replied he was building something more important, a stove that wouldn't kill its owners. Fellow trappers and homesteaders watched his preparations with bewilderment verging on mockery. Angus MacDonald, who trapped the neighboring valley, stopped by in June to find Jacob tempering steel springs in a carefully controlled oil bath. "You planning to shoe the devil's horses with those?" MacDonald joked, but Jacob just kept working, heating each spring to exactly the right temperature, cooling it at precisely calculated rates to achieve the flexibility his design required. The 3-year timeline wasn't arbitrary. Each component required months of experimentation. The floating plate connections needed to maintain perfect seals while allowing half an inch of movement. Too loose, and smoke would escape. Too tight, and thermal expansion would bind the joints. Jacob built and rebuilt prototype connections, testing them through hundreds of heating and cooling cycles. He created jigs and fixtures allowing consistent reproduction of successful designs, turning his cabin into a small-scale precision manufacturing facility. His notebooks from this period reveal meticulous attention to detail. Page after page of temperature recordings, stress calculations, and failed experiment analyses. He developed his own testing apparatus, using lever arms and weights to measure exactly how much force his joints could withstand before failing. When springs proved too weak, he learned to forge his own, using techniques borrowed from clockmakers. When standard rivets failed, he designed floating fasteners that could pivot under stress. The financial cost mounted beyond reason. Thomas pleaded with him to return to normal blacksmith work, to make horseshoes and tools that paid immediate dividends. But Jacob sold furs, traded labor, and borrowed money to continue his project. He ordered specialized drilling equipment from Denver to create precise holes for his expansion joints. He purchased measuring instruments accurate to thousandths of an inch, tools that belonged in Eastern factories, not frontier cabins. By late 1889, word had spread throughout the territory about the blacksmith trying to build an impossible stove. Some came to mock, others from genuine curiosity. They found a man surrounded by metal components that looked like nothing in any hardware catalog, octagonal plates with beveled edges, serpentine springs, joints that seemed to float in their mountings. The octagonal design emerged from months of calculation and experimentation. Jacob had discovered that 8-sided geometry distributed thermal stress more evenly than rectangular shapes, eliminating the corner concentrations that caused traditional stoves to crack. Each plate would be a separate casting, precision machined to interlock with its neighbors while maintaining independence of movement. On January 3, 1890, he began the actual construction that would either validate or destroy 3 years of preparation. The first challenge was casting plates with consistent thickness. Variation of even 1/16 of an inch would create weak points where stress could concentrate. Jacob built sand molds with unprecedented precision, using brass templates he had machined himself. Each plate required its own unique mold, as the octagonal shape meant no two were identical. The top and bottom plates were regular octagons, but the 8 side plates had to taper correctly to create the proper angles. He poured the iron at exactly 2600 degrees Fahrenheit, having learned that temperature control during casting affected the metal's grain structure. Too hot, and the iron became brittle. Too cool, and it wouldn't flow properly into the detailed edgework he had designed. Each plate featured a beveled edge with precisely machined grooves that would accept his floating seal. System: thin strips of flexible steel backed by ceramic fiber that could compress and expand while maintaining smoke-tight joints. The expansion joints represented the design's greatest innovation. Where traditional stoves welded or bolted plates rigidly together, Jacob created connections that could move in 3 dimensions. Each joint consisted of overlapping flanges held together by spring-loaded pins that passed through oversized holes. The pins could slide as plates expanded, rotate as angles changed, and compress as the entire structure breathed with temperature variations. He spent weeks perfecting the pin tension, strong enough to maintain structural integrity, but flexible enough to allow movement. The firebox assembly began in March 1890. Instead of a single casting, Jacob's firebox consisted of interlocking segments that could expand independently. The bottom plate featured channels for ash removal that doubled as expansion relief cuts. The side plates connected through a dovetail system that allowed horizontal movement while preventing vertical separation. Every connection point included his signature floating seals, creating what he called a structure that fights nothing. The most complex component was the smoke chamber, where hot gases collected before entering the chimney. Traditional designs used rigid baffles that often cracked from thermal cycling. Jacob created a series of overlapping plates suspended on spring mounts, allowing them to expand and contract while maintaining proper draft patterns. He calculated gas flow rates, ensuring his flexible design wouldn't compromise heating efficiency. By September 1890, the completed stove stood in his workshop 4 feet tall, octagonal, unlike anything the frontier had seen. Where traditional stoves appeared solid and immovable, Jacob's creation seemed almost alive, its plates shifting slightly even from the warmth of autumn sunshine. The springs and joints were hidden within decorative casting work, but careful observation revealed the subtle movement as metal responded to temperature changes. The first firing took place on October 15, 1890, with the mountain air crisp but not yet winter harsh. Jacob loaded kindling through the front port, watching smoke curl between the floating plates before finding its way up the chimney. As the fire built, he observed what 3 years of theory had predicted: the octagonal plates began to move. Not dramatically, just subtle shifts as metal expanded, each plate sliding against its neighbors while the spring-loaded seals maintained perfect closure. He measured surface temperatures obsessively during that first burn. The fire-facing surfaces reached 600 degrees, while the exterior remained below 200, a 400-degree differential that would have shattered traditional cast iron. But his plates simply adjusted, expanding where hot, contracting where cool, the spring joints accommodating every dimensional change. The stove literally breathed with the fire's rhythm, inhaling as flames rose, exhaling as they settled. The real test came with rapid temperature cycling. Jacob stoked the fire to maximum heat, then opened doors and windows to flood the cabin with below-zero air. The temperature differential spiked to nearly 700 degrees. In a rigid stove, this would cause immediate cracking. His octagonal plates shifted more dramatically, springs compressing and extending, joints sliding in their oversized holes. Metal pinged and whispered as it moved, but nothing broke. The seals held. The structure maintained integrity while accommodating stresses that destroyed conventional designs. Heat distribution proved remarkably even despite the moving parts. The flexible baffles in the smoke chamber created swirling patterns that extracted maximum heat from combustion gases. The octagonal shape eliminated cold corners common in rectangular stoves. Most surprisingly, the movement itself seemed to enhance heat distribution, as expanding plates created subtle air currents that circulated warmth throughout the cabin. November brought the first serious cold, temperatures dropping to -25. Jacob maintained a moderate fire and watched his creation perform. The exterior plates contracted significantly in the cold, but the spring joints simply extended to accommodate the shrinkage. The interior plates expanded normally from heat, creating a dimensional difference of nearly 3/4 of an inch between inner and outer surfaces. A rigid stove would have torn itself apart. His breathed deeper and kept burning. Thomas, initially skeptical, became convinced after witnessing a dramatic demonstration. During a -30 cold snap, Jacob deliberately thermal shocked the stove by throwing snow onto the hot exterior plates. Steam exploded from the contact, and the metal sang with stress, but the flexible design absorbed the shock. The plates shifted violently for a moment, springs working hard to maintain equilibrium, then settled back into their gentle breathing rhythm. Word spread through the valley about Harlan's breathing stove. Neighbors came to witness the impossible, a stove that moved. They watched the plates shift, heard the springs whisper, felt the even heat distribution. Some remained skeptical, insisting that stoves needed rigidity for durability. But as winter deepened and traditional stoves began their annual failure cycle, interest in Jacob's revolutionary design grew. The true test, however, would come with the kind of cold that Montana hadn't seen in decades. December 1890 brought a preview of nature's ultimate test. The temperature plunged to -48 degrees on December 22nd, cold enough to freeze mercury solid. Along Wolverine Creek, the familiar sounds of winter failure began sharp cracks in the night as stoves split, desperate hammering as homesteaders tried to seal growing gaps with tin patches, the abandonment of cabins as heating systems failed catastrophically. Willem Garrett lost his stove on Christmas Eve. The front plate developed a starring crack pattern where maximum stress concentrated, spreading like a spider web until the entire face fell away. He managed to contain the spilled fire, but his family spent Christmas huddled in blankets, burning furniture in a makeshift hearth. The Morrison family, 2 miles upstream, watched their stove's top plate warp upward, breaking the seal and filling their cabin with smoke. They fled to Fort Benton, another family defeated by thermal physics. Jacob documented each failure with scientific precision. He visited abandoned cabins, measuring crack patterns, calculating the exact stress points where iron had surrendered to temperature differentials. Every failure validated his design principles. Rigid connections created stress concentrations. Fixed geometry fought thermal expansion. Traditional stoves were engineered to resist movement, guaranteeing their destruction when movement became inevitable. His own stove continued its rhythmic breathing through the cold snap. The octagonal plates shifted more dramatically in extreme temperatures, sometimes moving enough to be visible from across the room. The springs worked harder, compressing and extending with audible whispers. But every joint held, every seal maintained integrity. While neighbors fought life and death battles with failing equipment, Jacob maintained comfortable temperatures with routine fire management. Marcus Sheffield, the territorial surveyor, visited on December 28th, specifically to observe the mechanical principles. An educated man with engineering knowledge, Sheffield spent hours studying the design. He measured plate movement, calculated stress distributions, and marveled at the elegance of Jacob's solutions. His subsequent report to the Territorial Development Board described a revolutionary approach to thermal management that contradicts established manufacturing principles while achieving superior results. The skeptics gradually became believers. Ernst Müller, a German ironworker who had mocked Jacob's flexible joints as weakness disguised as innovation, changed his position after examining the stress patterns in his own failed stove. The cracks followed exactly the paths Jacob had predicted, concentrating where rigid geometry created resistance to thermal movement. Müller publicly admitted his error, declaring that Harlan had solved the unsolvable problem. By January 1891, a stream of visitors came to study the breathing stove. Some took detailed notes, planning their own attempts at flexible designs. Others simply wanted to witness the impossible, a stove that survived conditions, destroying every conventional heating system in the territory. Jacob shared his knowledge freely, explaining the principles, demonstrating the movement, showing how flexibility created strength. But even he couldn't have predicted what February would bring. The weather patterns building in the Arctic were creating a perfect storm, a cold front that would challenge every assumption about survival. The breathing stove had passed every test. Now it would face conditions that existed at the very edge of human endurance. The Arctic Express that slammed into Montana on February 11, 1891, defied all recorded history. Weather stations designed to measure extreme cold failed when mercury froze at -39 degrees. Estimations based on alcohol thermometers suggested temperatures below -60. The cold arrived with explosive force, dropping 50 degrees in 3 hours. Windows shattered from thermal shock. Trees split with sounds like cannon fire as their sap froze instantly. Inside Jacob's cabin, the first indication of catastrophe came from the springs. They sang a high, metallic keening as thermal contraction pushed them to their limits. The octagonal plates pulled inward dramatically, gaps widening to nearly an inch before the flexible seals compressed to maintain closure. The entire stove seemed to shrink, fighting to accommodate stresses no designer had ever contemplated. Jacob fed it carefully, maintaining moderate heat rather than stoking maximum fire, understanding that extreme differentials might exceed even his design's capacity. The sounds of destruction echoed across the valley throughout that first night. Sharp reports like rifle shots marked each stove failure in neighboring cabins. The Williamson Place crack, the old Peterson homestead crack, the new arrivals from Ohio crack. Each sound meant another family fighting for survival with broken heating systems. By dawn, the only smoke still rising came from Jacob's chimney, a solitary plume in a valley of frozen death. Day 2 brought worse conditions. The cold intensified beyond measurement, beyond experience, beyond comprehension. Ice formed inside the cabin on any surface, not directly heated. Jacob's breathing stove labored harder than ever before, its movements violent enough to create audible sliding sounds as plates shifted. The bottom fire door gap cycled between completely closed and 3/4 of an inch open as metal fought to exist in 2 temperatures simultaneously. But the springs held, the seals maintained integrity, the fire never faltered. He documented everything with numb fingers in a cabin hovering at 45 degrees comfortable compared to the death outside, but still cold enough to make writing difficult. Day 3. Stove movement exceeds all previous observations. Estimate inch and quarter expansion differential between inner and outer plates. Spring number 4 shows signs of stress but maintains function. Ceramic seals performing beyond design specifications. Structure integrity complete despite forces that should theoretically destroy any metal construction. The ordeal stretched through 3 weeks of unbroken Arctic conditions. Jacob rationed wood carefully, understanding that gathering more meant certain death. He melted snow in pots for water, maintained minimal cooking fire, and trusted his revolutionary design to keep functioning. The stove breathed like a living thing, sometimes gasping with sudden contractions, sometimes sighing as plates found new equilibrium positions. The springs sang their stress song continuously, a metallic chorus of flexibility pushed to absolute limits. On February 28th, the temperature finally rose to -20 tropical by comparison. The rescue parties that fought through remaining drifts found devastation beyond comprehension. 17 dead along Wolverine Creek alone. Cabins with burst stoves, frozen families, desperate final messages scrawled on walls. At the valley's end, they found Jacob Harlan alive, tending his impossible stove, surrounded by the whisper of springs and sliding plates that had saved his life through conditions that shouldn't have been survivable. Professor Harrison Blake from the Montana School of Mines arrived on March 15, 1891, leading a team of engineers to study what newspapers called the miracle stove of Wolverine Creek. They found Jacob's cabin surrounded by the frozen remnants of catastrophe, failed homesteads marked by chimneys standing like gravestones. Inside, the octagonal stove still breathed with each fire cycle, its springs and joints whispering the secret of survival through impossible conditions. Blake's team spent 3 days documenting every aspect of the design. They measured spring tensions, calculated stress distributions, and marveled at solutions that contradicted established engineering doctrine. The floating seal system, combining flexible steel strips with ceramic fiber backing, maintained compression across temperature ranges that should have destroyed any gasket material. The octagonal geometry distributed forces in patterns their textbooks claimed were inferior to rectangular construction. Yet the evidence of success was undeniable. Harlan has intuited principles we're only beginning to understand mathematically, Blake wrote in his official report. His empirical approach to differential expansion accommodates stresses through controlled movement rather than resistance. Traditional engineering fights natural forces. This design cooperates with them. It's biomimetic architecture decades before the concept exists, a mechanical system that breathes like living tissue. Word of Blake's analysis spread through engineering circles and frontier communities simultaneously. The territorial legislature commissioned production drawings, making Jacob's design available to any blacksmith willing to attempt reproduction. The challenge lay not in understanding the principles, but in executing the precision required. Joints needed exact tolerances. Too tight, and they'd bind under expansion; too loose, and they'd leak smoke. Springs required specific tempers to maintain flexibility through extreme temperature cycles. Marcus Johansson in Helena built the first successful reproduction, taking 4 months to complete what Jacob had spent 3 years perfecting. His version saved the community hall during the brutal winter of 1892. The Copper State Mining Company commissioned industrial versions for their bunkhouses, scaling Jacob's octagonal design to heat larger spaces. By 1893, Harlan pattern stoves appeared in hardware catalogs, though few matched the original's precise engineering. The design influenced broader engineering philosophy throughout the Mountain West. Bridge builders began incorporating expansion accommodation beyond simple sliding joints. Railroad engineers studied the breathing stove when designing freight car connections for extreme temperature zones. The principle of cooperative flexibility, rather than resistant rigidity, found applications wherever materials faced severe thermal cycling. Lives saved mounted through subsequent winters. The February blizzard of 1894, nearly matching 1891 severity, claimed far fewer victims in areas where flexible stove designs had been adopted. Families who had invested in proper Harlan pattern stoves survived where traditional equipment failed. The Territorial Health Office credited improved heating technology with reducing winter mortality by 60% between 1891 and 1895. Most significantly, Jacob's design proved that frontier innovation could exceed established engineering practice. Without formal education or laboratory facilities, working purely from observation and logical deduction, he had solved a problem that killed hundreds across the American frontier. The breathing stove stands as testament to practical genius born from necessity, refined through obsession, and proven in the most extreme conditions nature could provide. In 2003, engineering students from Montana Tech discovered an original Harlan stove in an abandoned cabin near the ghost town of Garnet. After careful restoration, they subjected it to modern stress analysis using technologies Jacob could never have imagined. Computer modeling revealed that his intuitive design achieved stress distribution patterns that modern software would recommend for extreme thermal cycling applications. The octagonal geometry, dismissed by 19th century engineers as needlessly complex, proved optimal for eliminating stress concentration points. The students fired the restored stove through 100-degree temperature swings while monitoring with thermal cameras and strain gauges. After 113 years, the springs still functioned, the joints still slid, the plates still breathed. Material analysis showed that Jacob's specific iron alloy, achieved through trial and error, matched modern specifications for thermal cycling resistance. His heat treatment of the springs had created metal structures that maintained flexibility across temperature ranges exceeding design requirements in contemporary manufacturing. Jacob Harlan himself lived quietly after his revolutionary winter. He never patented the design, believing that life-saving knowledge belonged to everyone. He continued blacksmithing in Wolverine Creek until 1898, then moved to Butte, where he operated a small metalworking shop. He married Margaret Olson in 1899, raised 3 children, and rarely spoke of the stove that had saved his life. When asked about his engineering breakthrough, he would say simply, "Metal wants to move, I just let it." His influence on industrial design extended far beyond heating applications. The principle of accommodating forces rather than resisting them appeared in earthquake-resistant construction, expansion joints for bridges, and flexible couplings for machinery. The term Harlan joint entered engineering vocabulary, describing any connection designed to maintain integrity through movement rather than rigidity. Modern materials science recognizes his approach as pioneering understanding of fatigue resistance and thermal stress management. The last original Harlan pattern stove in daily use operates in the Granite County Historical Museum, fired every winter for demonstrations. Visitors watch the plates shift and springs compress, hearing the whisper of movement that saved dozens of lives. Engineers studying the design note, its elegance complex in principle but simple in function, achieving through mechanical sympathy what brute strength could never accomplish. The museum's placard reads, "This stove breathes so people could too." Jacob died in 1927 at age 78, his obituary, noting him as a local blacksmith and inventor. His grave marker in Butte's Mountain View Cemetery bears no mention of the engineering revolution he sparked. But in the restored cabins and historical sites across Montana, his breathing stoves continue their rhythmic movement, springs still singing, joints still sliding, proving that the impossible becomes possible when someone refuses to accept that the way things are is the way they must remain. The true legacy lies not in metal and springs, but in the principle itself. When faced with forces that destroy rigid systems, create flexibility. When confronted with stresses that break conventional solutions, designed for movement, the stove that learned to breathe taught engineers to stop fighting nature and start accommodating it, a lesson that saved lives then and continues saving them today in every structure designed to bend rather than break.